Hi, welcome to the Olympiad geometry. Let's continue our study on the radical axis. Before we start, if you think this video is helpful to you, please click the like button, comment, share, or subscribe the channel. Thank you. Let's see the problem. Let A, B, C, D be four distinct points on a line in that order. The circles with diameter AC and BD intersect at X and Y. The line XY meets BC at Z. Let P be a point on the line XY other than Z. The line CP intersects the circle with diameter AC at C and M, and the line BP intersects the circle with diameter BD at B and N. Prove that the lines AM, DN, XY are concurrent. This is a problem from IMO 1995. So if we just think about the problem, that it's asking us to prove that AM, XY, DN are concurrent. So if we extend YX and AM, DN, we want to prove they meet at a single point, right? Let's call this point to be Q. So how can we prove that three lines are concurrent? We first consider about that Q is an intersection point from AM, line AM and line DN, right? So we can extend AM, DN, and let AM, DN intersect at Q, right? Then we just need to prove that this Q is on XY. So we already know that XY is the radical axis of circle. Let's see, let's call the circle with diameter AC to be O1, the circle with diameter BD to be O2, right? We already know that XY is radical axis of circle O1 and circle O2. So if we want to prove that a point is on the radical axis of two circles, we simply just need to prove that this point has the same power to the two circles, right? So the power from Q, the power of Q to the circle O1 can be calculated as Qm times Qa, right? And the power from Q to the circle O2 can be calculated as Qn times Qd. We just need to prove these two powers are equal. I hope you are following me, that we actually transfer the problem from proving that three lines are concurrent to this writable equation, right? We just formulate it. It is important that we have something we can measure it, right? So now we want to prove that Qm times Qa equals to Qn times Qd. Then it becomes straightforward that if Qm times Qa equals to Qn times Qd, we know that equivalent to that triangle QMN is similar to triangle QDA, right? So we consider connecting this MN here, right? Connect MN here because angle AQD equals to angle MQN, right? So if QM times QA equals to QN times QD, we know that equivalent to the triangle QMN similar to triangle QDA, which means we just need to prove this one, right? To prove this one, we can just prove, because this circuit is the whole geometry is like a symmetrical problem, so we can just prove that angle QMN equals to angle QDA, right? We already know that angle AQD equals to angle MQN. So if we can prove that angle QMN equals to angle QDA, we prove this. These two triangles are similar, right? So we want to prove this angle equals to this angle. And look at here. We want to prove that this angle equals to this angle, right? If we connect BX, so here is the thing. We need to observe this figure a lot. Then we can find this relation, that this equation equivalent to this one. 180 minus angle QMN equals to 180 minus angle QDA. And we do the connection of XB, XD, and XN. I hope it's clear to you that the reason we want to connect XB, XN, and XD is that the angle BXD equals to 90 degrees, right? And the angle AMC equals to 90 degrees. So the reason we want to do this is that we want to prove this angle, the angle QMN equals to angle QDA, right? So A equivalent to 180 degrees minus angle QMN equals to 180 degrees minus angle QDA. 180 degrees minus angle QMN, that is this angle, right? The angle AMN, which is 90 degrees plus angle CMN, right? And 180 degrees minus angle QDA is 180 degrees minus angle NDA, right? NDB, right? Because angle NDB is inside the circle, so 180 degrees minus that one, we just need to find a quadrilateral inside a cyclic quadrilateral with the same circle, right? And here we find XBDN. So 180 degrees minus angle NDB equals to angle NXB, right? So here equals to angle AM, angle AMN, right? This one equals to angle MXB, right? We already know that angle AMN equals to 90 degrees, which is angle AMC plus angle CMN. And angle NXB, we want to find the 90 degree here first, so we can subtract this 90 degree out, right? And angle NXB equals to angle BXD, which is 90 degree, plus angle DXN, right? Equals to 90 degree plus angle NXD. Right? So basically, we just make this equation equivalent to prove that angle CMN equals to angle NXD. Right? So now we want to prove that angle CMN equals to angle NXD. Right? The angle NXD, look at here, angle NXD equals to angle NBD, right? Because XBDN are cyclic, so the equals to angle NBD. So we want to prove that angle CMN equals to angle NBD. Angle NBD is angle NBC, right? Equals to angle NBC. So we want to prove angle CMN equals to angle CBN, right? CMN equals to CBN. Here, basically we want to prove it equivalent to prove that CBMN are cyclic. Right, we want to prove these 4 points are cyclic. So we connect MB here, we connect CN here. To prove CBMN to be cyclic, we just need to prove that angle BMC, so this equivalent to prove angle BMC equals to angle BNC, right? How to prove it? It would be very simple then, right? Because P is a point on the radical axis, xy, right? So the power of P to circle O1 equals to the power of P to circle O2, which means MP times PC equals to PN times PB, right? This is a property that P is on the radical axis. And based on this, we already know that angle MPB equals to angle MPC, right? From these two equations, that this one can be rewritten as MP2 PN equals to PB2 PC, right? So MP2, that's MP times PC equals to PN times PB, right? So MP2 PN equals to PB2 PC, and we already know that angle MPB equals to angle MPC. So we know that triangle MPB is similar to triangle MPC, right? And based on this one, we just prove that angle BMC equals to angle BNC. Then we know that AM, XY, DN are concurrent. So if you look at the whole solution, it's not like very complex, it's not very long. But I feel this is not a like very easy problem. I think this is a medium to hard, medium to difficult level problem. It's IMO 1995. So you can see it's much easier than today's IMO problem, but not that easy. The whole idea here is that we transfer the target, like from the beginning we want to prove AM, XY, ND to be concurrent, right? And based on that, we need to find a way that we can write down a formula that we can look at. So the way is that we find the intersection point of AM and D first, that is Q. And we just need to prove that Q is on the XY because the XY is so special. It's a radical axis. So we can just write down the equation that we want to prove Qm times Qa equals to Qn times Qd. And based on that, we know that we can just transfer this target to be prove that triangle QMN similar to triangle QAD, right? That's one transfer. And then we already know that angle AQD equals to angle MQN. So we basically transfer this two triangle similarity problem to this angle equation that we want to prove angle QMN equals to angle QDA, right? And based on that, we translate it to we transfer it to prove that angle AMN equals to angle 180 minus angle NDB, which is angle NXB. I think that's a key point. This is not very straightforward to think about, right? But this is a key. Once we transfer it, then we already know that angle AMC is 90 degree, angle BXD is 90 degree. So we transfer it to prove the angle CMN equals to angle NXD, and which means that we want to prove angle CMN equals to angle NBC, which means that we want to prove BCMN to be a cyclic quadrilateral, which means, see, the figure is like a symmetrical stuff, right? We want to prove that these two angles to be equal. It's even difficult to prove that these two angles to be equal, right? So we choose another edge that we want to prove these two angles to be equal, right? And then it's clear because we already know that P is a point on the radical axis, so we can directly write down MP times PC equals to PN times PB, right? Therefore, we can prove these two angles to be equal, and we know that eventually the triangle QMN is similar to triangle QDA, right? Okay, I think this is a very interesting problem. I hope you like this problem. I hope you like the video. See you in next one. Thank you.